Welcome back to the deep dive. So you, our listener, are standing at a really crucial financial crossroads.
Hmm.
You're ready to invest in a brand new turn mill center. I mean, this is a machine that's going to define your shop's capabilities for the next decade.
A huge investment.
Huge. But before you sign that check, you hit this unavoidable dilemma. Do you commit to spending an extra, 30% of that capital budget for a true dedicated y-axis?
Or do you save the cash?
Exactly. Or do you opt for the interpolated system and just, hope you aren't sacrificing the rigidity you might need for some future complex job?
It's that classic anxiety of capital expenditure, isn't it? Because you're not just buying a machine for today, you're buying a set of limitations for the next 10 years.
That's a great way to put it.
Our mission today is to give you the clarity to make that call. We're going to stop thinking about this as just a feature choice and start thinking about it as a physics choice. We'll break down the fundamental mechanical difference, we'll look at how each system performs under a really heavy load, and, crucially, look at the long-term reliability.
So we're going from the hard iron, the core of the machine, to the clever software tricks and then back again.
Exactly. And here is the essential takeaway we want you to have right from the start. The choice is really defined by geometry.
Geometry.
Yes. If your future needs aggressive milling, especially complex features cut into the side of a part, you need a true Y, no question. But if 90% of your work is precision turning and you just need some simple features milled on the face,
Like a keyway or something.
or keyway, a flat, yeah, then the interpolated Y-axis might actually be your smarter financial move.
Okay, let's unpack that. I think we should start with the foundational hardware, because when we say true versus interpolated, it sounds like, confusing software jargon.
It does.
But the real difference is in the iron, isn't it? Whether the axis exists in the physical world or just in the software. Let's start with the easy one, the true y-axis.
The true Y-axis is very straightforward because it is a piece of real observable hardware.
You can see it, you can touch it.
You can see it. It's a physical independent slide. It has its own dedicated linear guides, its own ball screw, and its own servo motor.
So it works just like the X or the Z axis.
Yeah.
You command a move, and a physical mechanism actually slides perpendicular to the X-axis, giving you that clean XYZ coordinate system.
That's it, exactly. It's direct, it's robust, and it's inherently accurate because it's a standalone structure. Now, you'll notice on these machines, the travel for that true Y-axis is usually pretty limited.
Right, like plus or minus a few inches.
Maybe plus or minus 2 to 4 inches, yeah.
So why is that range so constrained? I mean, a normal VMC might give you 20 or 30 inches of Y travel.
Well, that's because the true Y-axis has to live inside a really constrained envelope. It has to be able to reach the spindle centerline, but it can't interfere with the machine's main job, which is heavy, large diameter turning. Its purpose is to provide rigidity for the tool block first and massive travel second. It's a support structure before it's a motion axis.
Got it. No, let's flip that. Let's look at the interpolated Y-axis. This is where the builder tries to save you money by using software to solve a mechanical problem. What is this clever trick actually doing?
It is a clever trick. I mean, it's often called polar coordinate interpolation. And the most important thing to get your head around is that there is no physical Y-slide.
None at all.
None. It's a virtual axis. It exists entirely inside the machine's control.
Okay, so if I'm at the control and I program a tool to move up, say, 10 millimeters in the Y direction, what's actually moving on the machine?
You're simultaneously using the linear motion of the X-axis and the rotary motion of the C-axis, so the spindle rotation.
The spindle itself is turning.
A little bit, yeah. The control calculates the exact combination of X position and C rotation to place the tool tip right where that Y coordinate needs to be. Think of it like trying to draw a straight line, but you can only do it by coordinating the angle of a pivoting arm and how fast you push it forward.
That sounds less like drawing a straight line and more like a high-stakes tightrope walk.
Yeah.
You're relying completely on the perfect instantaneous synchronization of two separate
non-orthogonal axes. Precisely. It simplifies the machine mechanically, which is where that 30% cost saving comes from.
Right.
But it also means that your Y position is totally dependent on the flawless operation of two systems that, weren't originally designed to work together to define that third axis.
So we've got the mechanics down, but that only matters when the chips start flying. Let's talk about rigidity.
The big one.
Yeah. If I'm doing serious aggressive milling, will the interpolated Y-axis just, break under the pressure?
Rigidity is the absolute crux of this decision. This is where the true y-axis earns every single penny of that extra 30%.
Because it's a dedicated slide.
Because it's a massive, dedicated physical slide, yes. It provides direct, unyielding support against cutting forces.
I'm picturing it like pushing against a solid brick wall.
That's a perfect image. You are pushing against a brick wall, and that lets the machine act more like a small, horizontal machining center when you're using live tools.
Okay.
So when you mill features into the side of a part, that lateral force from the cutter is absorbed directly by that dedicated structure. You can take deeper cuts, machine tougher materials.
Stainless in candle.
Exactly, without getting chatter or burning up your tools.
But what happens when that same heavy side-loading force hits the interpolated system? I mean, if the X and C axes are synchronized, shouldn't they hold the position?
They try. But the physics are, well, they're unforgiving. In an interpolated system, that side-loading force is resisted only by the combined efforts of the X-axis carriage and, critically, the C-axis spindle brake.
The brake. So you're not pushing against a solid beam anymore.
No, you're pushing against two synchronized clamps that are just trying to hold steady.
That's a very different picture.
It is. It's simply not as structurally sound. When you apply serious torque and lateral force from an aggressive end mill pass, that synchronized system is way more prone to deflection. You get these micro movements.
Wedges chatter.
Immediate chatter, poor surface finish, and dimensionally unstable features. You see things like tapered walls and pockets.
And that brings us to that anecdote you shared from the sources, the client who learned this lesson the hard way.
Yes, this client is the perfect example of the trap. They bought the interpolated machine specifically to save that upfront cost.
And for a while, it was fine.
For a while, it was perfect.
Yeah.
It handled their initial jobs. Simple off-center holes on the part faced no problem. But then 6 months later, they landed a profitable job that needed deep, tight tolerance pockets milled into the side of a shaft.
The complexity they hadn't planned for.
Exactly. And they immediately struggled. I mean, they were seeing tool deflection of several thousandths of an inch. The walls were tapered. The finishes looked like mountain ranges. The interpolated system, just relying on that spindle brake and the X-axis, it just could not lock down rigidly enough to maintain a perpendicular cut against that side load. They bought a limitation they didn't know they needed to avoid.
The conclusion seems pretty stark then.
It is. For aggressive side milling, the true y-axis is non-negotiable.
That really drives it home. It's not just a feature. It's an insurance policy for future work.
Mm-hmm.
But we can't ignore the money. That interpolated y-axis is cheaper. When is it the perfect cost-effective solution?
It absolutely has its place.
Yeah.
The interpolated y-axis shines when turning is the main event.
Right.
It's a fantastic choice if you want a shrewd done-in-one solution to streamline your process, but your milling needs are on the lighter side.
So we're talking about saving labor and secondary setups, not just the initial machine cost.
Absolutely. The main benefit is eliminating the time and labor of moving a part from a lathe to a mill for simple secondary work. That's a massive efficiency gain. And the system excels at features on the face of the part where the cutting forces are much lower.
Can you give us some concrete examples of those perfect tasks?
Sure. Think off-center drilling, milling a hexagon or a square on the end of a shaft, engraving part numbers, cutting simple flats, or maybe some keyways on the face of a flange.
Okay.
In those cases, the forces are pretty gentle, and the synchronized X and C axis can easily hold the coordinate. This is where you save that 30% upfront and gain enormous labor efficiency.
But what about tolerances, even on face work? If I need to hold, say, plus or minus half a thou on a milled feature, is the interpolated system reliable enough?
Ah, that's where the dependency of the system can become a risk. While it handles low force, holding really tight tolerances can be a challenge.
Why is that?
Well, the sources point out that because the virtual Y position relies on the health of the X and C axes, any minor issue, like thermal growth, can throw off the calculation.
So as the machine warms up.
As the machine warms up, the X-axis position might shift by just a few 10,000ths, and that instantly throws off your interpolated Y position by a corresponding amount.
So the interpolated system is really a tool for convenience and efficiency, perfect for saving those secondary setups, but we have to respect its limits, both for rigidity and for ultra-high precision.
Exactly. And that leads us perfectly into the long-term view. We're talking about a 10-year investment here.
Let's shift gears and talk about that long game. Maintenance and reliability. Now, the interpolated y-axis is mechanically simpler, fewer parts, fewer guides, fewer ball screws. Doesn't that mean it should be more reliable? Cheaper to maintain?
You would logically think so, and that is the trap. The maintenance profile is almost the inverse of the initial mechanical complexity.
Interesting. Walk us through the true y-axis maintenance first.
Okay, the true y-axis is mechanically more complex up front. It needs more lubrication checks, alignment checks, and you have another ball screw and servo to maintain.
Sure.
However, its major strength for long-term reliability is its independence. If your x-axis develops some minor wear or backlash after 5 years of heavy use, the y-axis accuracy is completely unaffected.
Because it's a totally separate structure.
It's a separate structure. It's inherently more stable and robust long-term for holding its original spec.
So a higher upfront maintenance burden, but more stability against wear and tear. Now, what about the mechanically simpler interpolated y-axis as it ages?
This is where its dependency becomes a liability. While it has fewer physical parts, its reliability hangs entirely on the perfect health and synchronization of the X and C axes.
So any wear or backlash in those systems.
Will directly and often unpredictably translate into an error in your virtual Y position.
So if the C-axis develops a little bit of slop, your Y-coordinate is immediately wrong. It's like relying on a synchronized swim team. But one of the swimmers is always a half-second late.
Perfect analogy. And let's bring back thermal drift. The source material notes that it's pretty common for an x-axis to shift by 1/1000th of an inch just in the first hour of running as the machine warms up.
And that immediately destabilizes the Y position.
Immediately. You are relying on software to constantly compensate for the physical world, and that compensation often requires more frequent and more costly calibration procedures just to keep the machine holding tolerance over its lifespan.
That's a critical point. You save 30% on the purchase, but you might be buying a lifetime of calibration headaches.
Yeah.
Especially if you want to run high precision or, unattended lights out jobs.
Precisely. That lack of independence is the reliability weakness. The true Y system maintains its integrity through brute physical force. The interpolated system relies on computational wizardry fighting against physics.
So what does this all boil down to for you, the listener, facing this decision right now? Let's recap that core trade-off one final time.
Okay. The true y-axis buys you rigidity, and it buys you future-proofing. It lets you confidently take on demanding side milling jobs, knowing that dedicated physical structure is going to oppose those cutting forces.
And it gives you long-term stability.
And long-term independent stability, reducing the risk of expensive calibration issues down the road.
And on the other hand, the interpolated y-axis buys you that substantial upfront cost saving. Plus, immediate efficiency gains for light face-based secondary ops, eliminating the need to move parts. But you have to accept the limitation. That complex side milling is probably out of reach, and that long-term accuracy is completely dependent on the perfect synchronized health of other axes.
Right. So we've established the interpolated system is mechanically simpler, but it relies completely on software and the condition of the X and C axes. This leaves you with the ultimate question as you make this major purchase.
And what's that?
When you're assessing this long-term investment, how do you quantify the risk of relying on software synchronization and the condition of other axes versus the initial higher cost of a completely independent, dedicated physical structure? That decision defines not just your budget today, but the geometric limits and precision capabilities you will live with for the next decade of manufacturing.